All right. We are live now. We're just going to make sure that all of our technical facilities are up and running. I'm going to do a quick check on Twitter to make sure I can hear me. Okay, check. Okay, and it looks like Twitter now does have video, which I didn't realize. So you guys all get to see our lovely faces. So if you've joined us, thanks for joining us today. We're going to talk about Blobstream Starknet and the milestone that the dev community of Starknet, the open source ecosystem, along with some of the exploration team members have hit. It's been an amazing project, an amazing integration with both Herodotus and Celestia. It's been an interesting architecture to come up with, and we could talk about some of the roadblocks and snags and how we've moved past them. So Blobstream Starknet itself it's an implementation or a re-implementation of some of the Solidity code bases on Ethereum layer 1. It's a Celestia. It's a one-way messaging bridge from Celestia to Starknet. The original way that we had conceptualized coming about this, it was about the same time that Celestia had talked about migrating fully to Blobstream X. And I'll let Diego talk a little bit about the difference between Blobstream X and Blobstream. And so we ended up going the route of using Herodotus. So to start today off, I'd like Diego to maybe give an overview of what a traditional Celestia rollup looks like, what it needs to commit to, and then we can talk a bit about what's been accomplished in Blobstream. So Diego.
Yeah, absolutely. So obviously the traditional way, quote unquote, you build the Celestia rollup depends on one, whether this rollup has a canonical bridge somewhere, aka it's settling to some other underlying layer, right? That's the case with what we're trying to accomplish here with Starknet L3s, for example. They settle to Starknet, for example. And then there's sovereign rollups, which we're not going to talk about today. And then the other difference is whether you are doing a CK rollup or an optimistic rollup, right? In the case of Starknet, we all know it's a CK rollup or a validity rollup. And in the traditional way, right, broadly speaking, without thinking about Starknet, but just thinking about CK rollups for a second, the way you essentially build a Celestia CK rollup or Validium slash Celestium, whatever you want to call them, is quote unquote straightforward. Like the idea is very simple. You just move from posting your state diffs or broadly speaking your data or batch data for your rollup, and instead of posting it to Ethereum, right, or to the same um, network that you're using for settlement, right, you would post it to Celestia, right? There's obviously a minor issue here if you just do that, which is that posting data to Celestia makes it available, but there's no way for the rollup system and thus for the underlying user to know whether this data was made available or not, right? They could run a Celestia like client and they could verify that, but there's no way for the rollup system itself to basically know when it should proceed with a batch or not, etc. And that's where the use of Blobstream comes in. Blobstream being the data attestation bridge that you can use to essentially build these like constructions, right? These like Validiums with Celestia DA. And what Blobstream does as a data attestation bridge is that it lets you bridge or transmit messages from Celestia to some other network, right? The original implementation was written in Solidity, and it had some caveats, let's just say. And eventually, instead of launching the first version that was built by a team member at Celestia Labs, we launched instead Blobstream X, which is the same thing as Blobstream in terms of like functionality and what it does. But instead of submitting a like long batch of Celestia headers and verifying a bunch of signatures, it uses CK, right, to verify all these like Celestia signatures with one proof. It's more efficient. It's more portable, let's say. And this was built by the team at Succinct. But yeah, like traditionally, it's very straightforward. You post your data to Celestia, and then you take whatever your settlement contracts are and hook those up to Blobstream, so that whenever your settlement contracts are verifying a batch and a validity proof for your rollup, you also verify one way or another whether the batch data for that specific like proof was posted on Celestia or not. And yeah, the obvious reason why we're here is to talk about how we kind of like migrated or built a version of this for Starknet, given that Blobstream was built in Solidity, and thus we had no way of like easily porting this to Starknet, right? But yeah.
Sweet. And then that transition to Blobstream X moves all of the signature verification off chain, right, into that snark.
Correct. It's if I recall correctly, it's a Plonky 3 circuit, and then the proof gets wrapped into Groth 16.
Awesome. Okay, so that kind of ties in nicely to the problem that we had with Blobstream Starknet, and you know, something that we'll talk about a little bit later today, which is Groth 16 is currently blocked on a syscall that basically needs to be implemented in our protocol stack, that Marcello has some cool alpha about later, but we couldn't go the full direct integration of basically you know, mimicking the succinct platform for proving those Groth 16 circuits, which would kind of lead to a clean architecture of basically just having exactly what Blobstream X does on L1 and port that to L2. So since that infrastructure is already stood up for relaying and proving those block header batches to L1, we essentially needed to appeal to the L1 and get the information and the data commitments from L1 where it's already doing the work. You know, it's the same data commitments that need to be proved on L1 as L2. You know, up to L2. So that's where we needed Herodotus to come in, and we basically use Herodotus storage proofs to prove what's going on the L1 and prove the storage slots that reflect the actual data commitments for the Celestia Blobstream X on L1, where it's actually already doing the work, up to L2 with the storage proofs. And it's a pretty cool architecture. There's a little bit of latency built in just because we do have to, you know, route from L1 to L2. But, you know, overall, Herodotus storage proofs have kind of unblocked us, at least in the short term, until that syscall comes about. So yeah, Marcello, if you could maybe talk about, you know, how unique architectures like this come about and how the storage proofs facilitate it, that'd be awesome.
Sure. So thanks for giving the introduction. Maybe first I'll talk about what even makes storage proofs possible.
Cool.
So first of all, like, let's remind ourselves how block trees are constructed. So whenever we verify the consensus, okay, we run that lifeline. At the end of the day, just agreeing what is the latest state root, which eventually gets committed to the block hash. In the EVM, we have like opcodes that allow you to access the block hash, and as long as you trust that block hash, it also means that you trust the validator set of Ethereum. And that block hash, in a sense, commits to the full history of the chain because there is like a full linkage. And also the block hash is a hash of a block header, and the block header contains the state root. So now that said, it means that as long as you have enough compute to, well, run a bunch of hashes, you can verify the inclusion of either any piece of data ever present on Ethereum. And by piece of data, I mean from state, accounts, receipts, block headers, pretty much everything that was ever seen on the chain. And that's like the idea that makes storage proofs possible. But there is one caveat. It's really expensive to do it, especially directly on-chain. So this is why we use ZK to basically do this heavy computation off-chain, and then on-chain just verify the proofs of doing so. And now how this is applicable to layer 2s. So like I said at the beginning, the full commitment to the history of the chain is this one block hash. So what if we can send, using the canonical bridge, this one block hash to some layer 2, and then given the capability, the computational capabilities of, let's say, Starknet, or also like we can just verify these proofs directly, there we effectively make layer 2s not just like some platform that derives the security of layer 1, but kind of an extension of layer 1 because it gets access to its own state. So that's what storage proofs do. And now how this is applicable in this context, whenever Blobstream X proof gets verified on layer 1, we don't have to re-verify it on layer 2 because we can just use the fact that, hey, this proof has been verified on layer 1. So let's just access the result of this verification on the layer 2. That's basically where we step in.
Awesome. Cool. Well, at the end of the day, Blobstream Starknet is essentially a tool to enable L3s. So we do still need to have an integration, and I just talked to Elias at Kakarot, so we'll be doing kind of the fine tuning of the integration with those guys over there. But yeah, I want to talk a little bit more about the broad scale application of Blobstream Starknet and L3s in general. One of the things that we obviously need is some of the things Diego mentioned, which is, okay, now we have a commitment to a state root that reflects a state diff. But how do we prove it? How do we prove that the Starknet OS actually ran the right computation? So some of the cool work that's been done on the Herodotus side, especially, is the Cairo verifier. So if you look instead of the perspective of the actual Blobstream Starknet contract and move out to the actual app chain itself, the app chain itself will need to run the Starknet OS and re-execute all the transactions and come and output two things: an execution trace to send to the Stark prover, and the state diff to basically post to Celestia. And we need to tie those things together. So Marcello, do you want to talk a bit about the Cairo verifier and how it plays into all of this?
Sure. So yeah, I mentioned proofs already, and like with ZK we can build cool stuff such as, for example, ZK rollups, because what a ZK rollup is, depending on the model, but effectively we have some runtime that either relies or not on some ZK VM. We run some computation, and part of that computation is also writing and reading to some state that we manage, and this is a ZK rollup. But the bottom line is that eventually just some proven computation. But of course, when we have the trace, we put it into some prover, we get the proof, but this proof has to be verified. And as of today, the only existing on-chain verifier for Stark proofs generated by the Stone prover, was existing on L1 and was implemented in Solidity. So, well, how do you build layer 3, right? Because you have to verify also these proofs on Starknet in that case. So that's effectively the work that we did. So we got some inspiration from the implementation in Cairo 0 of such a verifier, which is used internally by Sharp to do recursion. We re-implemented the same logic in Cairo 1. Of course, with a few caveats, we changed a little bit the architecture. But yeah, now effectively you can take any Cairo program, such as, for example, Starknet OS, pass it through Stone, prove it, take the proof, verify it on chain, and you have the usual logic and abstraction behind the fax registry and so on. So that's what we recently built.
Amazing. And yeah, that'll obviously be one of the crucial pieces to actually implement this in an entire app chain stack. So it's awesome that that's available today. Some of the things that's not available today, but that are super interesting, is some of the equivalency services that Celestia has been working on. Diego, I wonder if you could talk a bit about, maybe the future of Blobstream Starknet, or kind of architectures that this can potentially go.
Yeah. So I mean, now that Blobstream Starknet is like a thing, right? Like the community has done a great job at like bringing it essentially to fruition, right? And we have a way to um, relay or read these like data commitments from Blobstream X on layer 1 on Starknet, right? And we already also have the integration with stacks like Madara that simply read and write data using a Celestia Light node. The missing component here to like make this like essentially a full end-to-end implementation, like you mentioned, would be to essentially verify, right, that the data posted to Celestia corresponds to the state diffs or well, the commitment to the state diffs that goes into Starknet OS, right? And then in that case, there's like, as far as I know, there's like two ways that you can go about it, right? One way is to take your rollup program, right, which in this case is like Starknet OS, and you would add whatever necessary modification you need to add in order to essentially um, ingest the Celestia blob commitment to your data, which is your state diffs, and inside of Starknet OS, verify that whatever commitment you have for your data, right, be it for Celestia or for anything else, matches the commitment of your data that is used internally on Starknet OS, right? That's the Poseidon or Pedersen tree, if I recall correctly. That's one way to go about it, right? The other way, which in which you could like finish this like integration without having to modify Starknet OS, would be to essentially prove equivalency of the commitments that Starknet OS does to your data, but essentially at the settlement layer or at the settlement level per se. So the previous approach, right, does everything like essentially inside of the rollup, and you could think about it almost like aggregating proofs, if you will. It's in a certain sense like simpler to think about or reason about, because now you just think about it as like, okay, I modified Madara, I modified Starknet OS, or added this like verification, and I use Blobstream with my settlement contracts, which would be something like a Piltover, right? And now you're good. With the other approach, you would, for example, spin up your Madara chain, right, to write batches of data to Celestia, read them. You would still use Piltover. You would still use Blobstream to verify that the data routes to which you committed your data to are available on Celestia, right? But then there's the missing piece, right? That from step one that you could have done in Starknet OS, right? And the way you do this is by proving equivalency between the two commitments, right? The Poseidon / Pedersen tree for Starknet and the Celestia blob commitment. And what you can do is prove this off chain, right? So you would run this with whatever logic you want, right? You could currently the work that has been done by CNode at Celestia Labs has been in RISC-0, but you could perfectly do this as well in Cairo, right? Like Marcello mentioned, like you could run, for example, like a stone prover, and you could write this like equivalency service as a Cairo program, run it off chain, verify it on chain, right? And you would just like hook that into the logic of like your settlement contracts, so that you know that that the sequencer / batch poster / whatever you want to call the node that posts data has made the data available, right? And that way you don't have to like essentially get your like funds frozen, right? That's like the security assumptions of like Validiums. So with this different like approach, you would still obviously in the same way that an L3 does, you would still run this computation off chain, but it doesn't require modifications to Starknet OS. It does obviously require having to like write this equivalency service either in Cairo so that it can be verified with the Herodotus integrity contracts or program circuits, if you will, or it would or in a similar way to the I guess like Blobstream on Starknet v2, it would require the BN parents, right, like the syscall, to be able to like efficiently verify like Grot16 proofs, because the current implementation of the equivalency service is built with RISC-0, and you would wrap those proofs into Grot16. Just as an example, And yeah, like it's hard to say which one is better ultimately. To make that decision, both of these have to be built, right? And then you have to do some benchmarking, take into account infrastructure costs, gas costs, etc. But the options are plenty, basically.
Well, that's kind of interesting because, and I'm glad you mentioned Piltover, because Piltover is a project that kind of spun out of Blobstream Starknet, just because it's kind of an obvious part of the app chain stack. So Piltover is part of the Twitter thread announcement. I encourage you to go check it out. What it is it's the core contracts, basically transposed to Cairo. Um, but one of the things that those will, free us up to do is experimentation. I mean, those will essentially let us basically not be locked into this is exactly how the update state function works for these app chains, but here are 5 different ways the update state function can work on in the Cairo code for these app chains. Pick whatever is right for your customizable app chain. So especially devs listening to this call, open source devs, we definitely love some contribution on Piltover. But all of those different varying architectures that Diego said, we can basically have a trait that has an overall description of what needs to be done in that update state, and then be able to implement it in a variety of ways. Cool. I mean, that's kind of the last thing I had. Do you guys have any other topics or pieces of conversation or questions, or do we leave anything open-ended? What do you think, fellas?
I mean, I guess it would be interesting to chat about, like, well, why would someone build a Starknet L3, right? And like, why a Validium, I guess, right? Like that's something that maybe we might be missing from this overall conversation, right? Like, what does this all accomplish, really, right?
Yeah, I mean that's kind of like first principles, right? Like,
Yeah.
what are we even doing here? Yeah, I've gone back and forth about that a bunch in my head. I mean, the stock answer is customizability, hyper throughput. Um, you're always going to get some pushback from cynics that like, well, just use a database. You know what I mean? Like, but I do believe. I mean, you are maybe lessening the trust assumptions as you walk up the stack, but you still gain security and trust from the stack beneath you in anything you're doing in blockchain. So I see value in it there with customization, the security gain, and yeah, hyper throughput or hyper scale. What do you guys think?
I mean, I think for like once, right, you can essentially build your application, right, that you would have otherwise built on Starknet, but as your own like rollup or Validium, right? You're still part of the like Starknet ecosystem. There's like a lot of things that you can like experiment with. Hopefully, once we have like versions of this that can be like run on testnets, right? Like there's like the low hanging fruits, right? Like having like a Kakara L3 or Kakara Validium right on top of Starknet. I think if when you combine the sort of like provable VM paradigm of like Starknet, right, with the verifiability and overall like cost reduction that like things like Celestia afford you, you can actually you have more room to experiment, right? I say this as somebody that before working at Celestia Labs worked as a smart contract developer, and I worked on an application that was on the L1, and it's always like bothersome when you're thinking about like what you're gonna build, and you're like, wow, this is so cool, it's gonna be so dope, and then you realize like, oh, it's gonna cost like way too much money, right? Like, or not just to like the developer deploy it, but like more so like who's going to use this if like each interaction is like $200,
Right,
right?
right.
And that's with low gas fees, right? obviously L2 solve this issue of like overall like gas fees on the Ethereum ecosystem, right? But when you have things like L3s or like Validiums, right, where you're no longer posting the data to Ethereum, even after EIP 4844, which has done a good job at like reducing fees, you're now talking about like essentially like almost like zero fees, right? And in my opinion, the good thing about this combination is that you're building L3s that like are verifiable, right? Like they actually have proofs, right? There's no dangerous games that are being played with like trust assumptions. And yeah, I mean, I'm overall excited to see not just things like Kakarot like experiment with like Validiums and starting L3s, or well, Validiums that are L3s. I don't know. The wording gets complicated, but things like Gisa, things like Dojo, etc., especially like on-chain games, like provable on-chain games, really like I feel like benefit from like this overall like scheme that or architecture that's like being built with Madara and like Validiums.
For sure. There's almost like a if you build it, they will come thing where like, we don't even know the coolest things that will be built on an app chain yet. Once it's here, Dojo and Cartridge have thrown out crazy ideas, just like, an entire autonomous world in an app chain on a click of a button, that kind of stuff. If you build it, they will come.
Yeah, maybe one more reason to build layer 3, in my opinion, is that, like Diego, you observed, like whenever you have an application deployed like a layer 2, it's, I think, kind of natural to transition to an L3 at some point, for many reasons. I think, in my opinion, the most notable reason is that suppose that you build something amazing, but someone else also built something amazing, which is getting a lot of traction, let's say on layer 1, driving up the gas fees, and you're also affected, right? Eventually. And well, it also runs on the same sequencer if it's running both applications on the same layer 2, and you kind of run into the noisy neighbor problem.
Yep.
And with like in layer 3, you work in complete isolation. You can settle whenever you want. When gas is cheap, you basically control your stack. And I think that's super valuable because you can abstract so many things from your users. Just because of that, it's probably worth it.
No, absolutely. And I mean, like, there's a bunch of other stuff that like started coming into my head, right? Like oracles like Pragma, right? That are, if I recall correctly, building L3s on Starknet, right? And a lot of like applications that like benefit from not just the provable VM or Cairo VM, right? But they also benefit from like cost reduction, but more importantly, like verifiability. Like, I think that's like the reason why, without trying to like be biased, like you would choose something like Celestia DA, or you would choose like Alt DA that's not essentially an AWS S3 bucket that 10 people sign over. Like you want to have at least some form of like security guarantees, right, if you will.
Yeah, and as far as the use case of some type of control over your rollup stack and not running into the noisy neighbor problem, it seems to me like that's basically been proved out. You have things like DYDX, Paradex, these things that have created massive amounts of volume, that they don't have to worry about the noisy neighbor. The only thing this is doing it is basically opening that stack to anybody who wants to deploy it.
Yeah.
Which is pretty powerful. Cool. Cool. Anything else you guys have?
I think maybe it's worth to talk about like also the verification of the Graph 16 proofs on Starknet. I think we didn't cover that. But yeah, there is a project called Garaga, which we have the pleasure to be contributors to as well. And yeah, basically soon, I think around the summer, there is a chance that this will be available on Starknet. But also, maybe here I could say something pretty weird. But actually today, it's even possible to already have Blobstream X, in my opinion, because you can prove the execution of Garaga, which requires some hints. You can prove it. You can just prove it with Stone and then verify like Stone proofs on Starknet, which is also potentially like an interesting architecture. And you can batch proofs together, which is even funny.
Okay, let me ask you a question. Okay, so one of the things that Groth16 opens up is that cleaner architecture of basically verifying the succinct X. Diego, if you don't mind muting, or maybe I can do it. So basically verifying the Groth16 proof of succinct X platform, which is what what is it called? Grok? No. There's some Solidity library that does it for L1. It basically auto generates the function verifier on. Yeah, thank you. So on L2, if we unblock this pairing, we can essentially do this function gateway, which is succinct succinct's platform in Solidity, where anyone can go auto generate a function verifier for Groth16, and then they can basically prove whatever their circuit is proving. That's actually what Blobstream X is actually one implementation of a function verifier in the succinct gateway. So maybe Marcelo, can you walk through like it? Originally, what we were thinking is that once that Groth16 gets unblocked on Starknet, we would just implement it in Cairo. But if we did it with this way, what would that architecture look like?
I mean, as of today, it's changing a bit because there is a new built-in being added to Cairo, which is very specifically like modular arithmetic, and this is not yet supported by Stone, I believe. But that's a good question to some Starkware folks. But yeah, like in previous version, it was possible, from what I recall, to just prove it, with normal Cairo. Then you throw it into Stone, and voila, we have a Stark proof that proves the verification of the Groth16 proof. So that was possible, but I think right now with this new syscall, just do it directly. There is no need to wrap it. But it's maybe gonna enable like lower latency. But the question is also gonna be around the cost, because maybe it will be the case that it's still cheaper to verify a storage proof. It really depends.
Interesting. Cool.
But you can also aggregate, right? You can generate a Stark proof that proves the execution of many Groth16 proofs. Yeah, there is like a lot of designs that can be used here.
Yeah.
So you said, yeah.
I just wanted to add one thing to think about, right, is that so there's like this like V2, right, of Blobstream X, where you are verifying the already existing Blobstream X proof on Cairo through like Groth16 and Grog and whatnot. And obviously that has the benefit of like now it shares the same proof as like the Ethereum 1 version, etc. But there is also the possibility. I'm not saying it's like a simple task, but you could build Blobstream X, or the logic underneath Blobstream X, which is Tendermint X, as a Cairo program. Given that if you were to put side by side like Blobstream and Blobstream X, like the main difference is like how you verify that like a data commitment or a batch of headers is valid, right? In V1, it's like you have to loop through signatures and verify all those. In Blobstream X, right, you verify this like Groth16 proof of the Plonky 3 proof, or sorry, Plonky 2 proof, and that's it, right? So you could in maybe like a V3 or V2.5, I don't know. You could try to build Tendermint X, right? But using Cairo, and that way you no longer need to like wait for this pairing. You could verify it with integrity. But another thing about Tendermint X, right, is that like it's used for Blobstream, and that would help a lot with Blobstream X. But because Tendermint X is proving Tendermint consensus, right, you could, for example, use this for other applications that might want to talk with other or interact with other Cosmos-based like chains, right, or chains that use Tendermint under the hood, basically. I think that's like worth exploring in the future.
Yeah, definitely. Like Cairo is really powerful. It's a zkVM. You can do quite a lot of stuff with it. So literally nothing prevents you from implementing a program that just verifies a bunch of signature and then call it consensus verification. I guess you can do it. The question is, what's going to be the benefit of that? Like, probably you avoid going through Graph16, so you don't need to generate a Graph16 proof, which probably takes a while. You just go directly through a Stark. Yeah, there's a lot of possibilities. The question
Worth
is it
benchmarking,
is it actually worth it?
Yeah.
Let's build it. Let's see. Sweet. This has been an awesome conversation, guys. Yeah, I want to thank Marcello for joining. I want to thank Diego for joining, and thank both you guys for helping with the integration to where we're at. There's obviously a lot of exciting work to be done, like we've kind of just talked about. A lot of avenues to take, a lot of code to write. So if you are listening to this and you're a dev, we would love to have you. The repo is github.com, keep Starknet strange, Blobstream Starknet. And you can also find us on Twitter or on Telegram. So yeah, once again, thank you guys. Really appreciate it. This has been awesome. And have a great afternoon or evening.
Thanks.
Have a good one.
Bye.